Hello everybody. Today we're going to look at examples of the log function. That's our mission today, is to look at the examples of the log function and their derivatives. I have selected a few examples for us to work on to help us understand about the log functions and their associated derivatives. So we start with y equals the natural log of x to the fourth plus 3 in parentheses squared. And for this function, we would like to know its derivative. To do that, we have to look at what I call what function is the last thing a computer would do. Because if you care, what I'm stalling on and what I'm trying to pause on to give you a chance to think about is what we have here is a parentheses power. That looks like a chain rule. But because that's tucked inside of a log, you actually have to do the log rule first. The rule that I used the first is the last operation the calculator would do. And looking at these brackets, the log would be the last thing you would press on your calculator. If you do it through, if you plugged in a number, just think about plugging in a number. When you plug in 1, it'd be 1 to the fourth plus 3. You'd get that first. Then you would square it. Then you would take the log of it. That tells me the first rule I got to do is the log rule. Well, the derivative of a log is the derivative of the inside over the inside. So I'm going to write the inside down now. So there's the inside. All right, that's the inside of the log. Now I need the derivative of the inside of the log. Well, look at that expression in the denominator. That's really what I'm doing. I'm taking my time. I need the derivative of the denominator. Well, to take the derivative of the denominator, it's a parentheses power. It's another chain rule. What you would do is bring the 2 down, leave the inside alone because that's part of the chain rule, subtract 1 from the exponent, times the derivative of the inside of that expression because that's the chain rule. And so there is my derivative. So again, recall, that's my u. This is all my u prime when it comes to the derivative of the log. The derivative of the log is u prime over u. And so now we have to simplify. The good news, if you just keenly look at it, you have an x to the fourth plus 3 in the top and an x to the fourth plus 3 squared in the bottom. One of them will cancel. And so really you have 2 times 4x cubed all over x to the fourth plus 3. Again, I canceled an x to the fourth plus 3 because I have 1 here, 2 here. Good cancellation leaves 1 in the bottom. Last but not least, you can multiply the 2 and 4 to make 8x cubed. And so this is my simplified derivative. From here, what would you like me to do? If you'd like me to find the slope, there it is. I just need to plug in the number. Recall, what's the next steps you can be asked? Well, you could be asked to find the slope at x equals 1. No big deal. Plug in the 1 and you get 8 times, is that cubed? Yep, 8 times 1 cubed over 1 to the fourth plus 3. And doing simple math, you get 8 over 3. Boom shakalaka. You now have the slope at x equals 1. And the slope is important because that'll determine if I'm increasing or decreasing there. And since the slope is positive, I know my function is increasing there. So we can utilize all the things we've learned in previous videos and apply them to logs and exponential functions. Today we're just working on logs. My next video will work on exponentials. So that's our first example. Let me just kind of highlight this out as done. All right, let's move on. Let's do this again though. Let's say we have a function and it is parentheses log of x to the fourth. I really want to make it clear how you attack this. Now, please notice this is different than the previous one. The parentheses is on the outside. Notice this. The last operation now would be what? Say it with me. The power, right? Plug in a calculator like 2. It would do the natural log of 2 first, and then you'd raise that to the 4th. Since the power is the last operation, that's actually the first rule I'm going to apply when I take the derivative. So in this example, and that's why I did these examples back to back, the previous one and this one, if I want the derivative of this expression, I would bring the 4 down, leave the inside alone. You've heard me say that before in the chain rule. Subtract 1 from the exponent. So that's the power rule, right, guys? Generalized power rule. Bring the power down, leave the inside alone, subtract 1 from the exponent. Now, we got to multiply by the derivative of the inside. Well, the inside is the ln of x. The derivative of the ln of x is the derivative of x, which is 1 over x. And so this is my derivative. Again, different. Notice, allow me to scroll up, this power was inside the log. So I did the log derivative first. This power is on the outside of the log. I had to do the power first. And so to simplify this, there's not much to do. Just going to make it a fraction. 4 natural log of x. Make sure that cube is on the outside. It's very important when you type it into computer programs. That cube is on the outside of the log over x. And there is my derivative. What are we doing with it? Well, again, you want the slope? There you go. You want the rate of change? The rate of change at x equals 3? No big deal. Plug in. You got to remember why we look at the derivative in the first place. The slope is one thing we use, and the second is the rate of change. So the rate of change, well, we just plug in, and we would get 4 times the natural log of 3 cubed over 3. And me and my calculator would just get us an answer. That's all I need to know. The rate of change is whatever this number is. If the rate of change is positive, that means we have an increase in growth. If the rate of change is negative, that means we have a decrease in growth. Cool. We did those examples to show you the difference between how you would attack a problem if the power was on the outside or if the power was in the inside of the log. And that's very important when you're looking at these rules, especially with log. The bottom line, you just got to be careful when you're dealing with log functions. So let's step this up. Let's say I want to graph y equals x squared ln of x. And I shouldn't say graph. All I care about is finding the max mins. Let's get back into the game again. How, if this is my profit function, what would be the maximum profit? If this is my cost function, what's the minimum cost? If this is my productivity values, where is maximum productivity? So these, I always care about max and mins. This is one of the biggest things we do when we do the derivative. We analyze for max and mins. Very important to us in all disciplines. So once again, we got to review how to find a max or min. Say it with me now, guys. Derivative equal to 0. So let's do this. Derivative. Good. This is a good review from a previous video. If you ever have anything in front of a log that's a variable, you need a product rule. And so here we go. Product rule time. U prime v plus u v prime, or in some order very similar. So u prime v, so I'm going to write my v in there, natural log of x, plus u v prime. You can look at my previous videos on product rule to see how I do it. It's very similar to everybody else's approach. So the derivative of x squared goes into there. No big deal. 2x. The derivative of ln of x goes into there, because that's the product rule. The derivative of ln of x is the derivative of the inside, 1 over the inside. And so there is my derivative by the product rule. Again, how did I know it was a product rule? Whenever there's a function in front of natural log, it is a product rule. What's a function? Pretty much everything. The only thing that would stop this would be if there's a number in front. If there was a number in front, you would just do the derivative of the log. As soon as there's a variable in front, welcome to the product rule. All right, so we did the product rule. Let me clean this up a little bit. You have 2x ln of x. Now, good algebra. X squared. Get my green here. What's going on? Okay, fine. It doesn't want to use green. I'll use red. So I would like to simplify this. Apologize for the tablet issue. It happens. So I would like to simplify this. The x squared times 1 over x, well, x squared times 1 over x is x. Think about that. X squared divided by x is 1x. So there's my derivative. All right, guys. So now we move on. Once you get the derivative, you set it equal to 0, because we've done this before. To find a max or min, these are the critical points. To find critical points, you take the derivative equal to 0. So I'm going to set this expression equal to 0. So now I have to use algebra, or in this case, I have to do my exponential or logarithmic rules to solve this. My first step, I'm going to subtract the x over. So I have 2x. Do I want to do it that way? You know what? I'm going to pause on that. I don't like that approach. I was going to do it one way. I don't like it as much. Instead, I'm going to factor an x out. I think that makes more sense, and I get to what I want. Factoring is always a tool, and we've used it over and over, so might as well use a tool that you guys are comfortable with. Notice that both expressions have an x, so I factored that out. Also, I'm afraid you might miss one of the critical points. X can be 0, or 2 ln of x plus 1 can be 0. How do I solve that? Subtract the 1, divide the 2. Ln of x equals negative 1/2. Because, right, subtract the 1 to divide the 2. Now we have to have good exponential skills. If the natural log of x equals negative 1/2, to get rid of the natural log, you would exponent both sides. And when you take the exponential on both sides, you're left with x equals e to the negative 1/2. Again, the only way to get rid of a natural log is to e both sides. And that's what I did. To get rid of a natural log, I took the exponential of both sides. And that's how I arrive at this solution. So what I have here is on my number line, I have 0 and this number e to the negative 1/2. Just so I have an idea of what that is, I am going to my calculator right now and finding e raised to the negative 1/2. And I get 0.6. So this is roughly 0.6. I need to know roughly where this thing is because I need to pick numbers in between, before, and after. So like negative 1, no big deal. Here, 0.5 will work. And here, 3 will work. Again, remember, you can pick randomly. And remember, we plug that into the derivative. All those values will be plugged into the derivative, 2x ln of x plus x. So if I plug in a negative 1, well, here's the thing. The natural log function is not defined for numbers before 0. So we have a natural cutoff phenomenon here. Anything before 0 does not exist in the natural log, okay? The natural log actually doesn't even exist at 0. The natural log of 0 does not exist. The natural log only exists for positive numbers. So I automatically have what I call is a natural log, or not a natural log, but a natural bound. It is a natural log bound too, but ha ha ha. It is a natural bound. It's a natural bound because the natural log is not defined at number 0 and below. All right, no big deal. It just means I don't care about negative 1 anymore. That was just a point to plug in, but now I know I'm stopped here. There is no upper bound here. This can go forever. This is not an absolute extrema question. I don't have an upper bound, okay? So I can go forever in this problem. So now I need to plug in 1/2 and 3 into this expression. So just give me a second. 2 times 1/2 is 1. 1 times the natural log of 1/2 is negative 69 plus 0.5 gives me a negative number. So I have a negative number. When I plug in 3, the good news is natural log of 3 has finally turned positive. So this is positive plus positive, and we are officially at a positive. Get your definitions out. The derivative is negative means you're decreasing. Know your definitions, people. If your derivative is positive, you're increasing, which means this right here is a minimum. Because if you go from decreasing to increasing, you're at a minimum. And so my minimum is when x equals e to the negative 1/2. You cannot put it in as a decimal unless it says you can round. Most times you have to leave it in its proper form. Understand, if it asks for a point, you need to go back to the function and plug it in. You actually need to take this back to the original function, now, and plug it in. I'll allow you to do that on your own. So what we found was, for this expression, we had one minimum and no maximums. You could look at 0, but the problem is, again, you can't. There is no graph at 0. There is an issue at 0, okay? Again, when you plug 0 in the derivative, you cannot do that. That is not allowed. So there will be no value there. Excellent. So max and mins are always the same. Just a recap. You take the function, you take the derivative, knowing it's a product, because we said anything in front of a log is a product rule. So derivative equal to 0. I always have my friend factoring to help me. If it wasn't factoring, I might have subtracted the x and done some other algebra. But this was clearly a factoring example. I pull it out of an x. Doing that allowed me to solve for both of these points. Understand, to get rid of a log, again, you need the e. And that's what happened there. Alrighty, let's look at one more problem. So let's say we have the following. I believe that's a price function. Nope, that's the supply function. So I'm looking at the supply function, which is still a price function. So the price, when it comes to supply, is modeled by the following equation. So this is the supply equation. Where we will supply X units at the price P. You'll supply X units at price P. That's exactly what this would do. So 10 plus 50, ln of 3x plus 1 is the function where, again, if you plug in X number of units, will tell you the price that it needs to be set at in order for us to supply that number of units. It's our pricing equation for us to supply our product. So the question we have is the rate of change of price with respect to units. That's what we want to find. We want the rate of change of price with respect to units. So rate of change of price with respect to units. Well, rate of change means we're going to take the derivative. In this case, it's going to be the derivative of price with respect to units. That's why I got to read this a couple times. Rate of change means time for the derivative. It's the derivative of price with respect to is really that denominator letter, which means we want the derivative of price with respect to x. That's the symbol we need here, dp dx. So how would we find dp dx? The good news is we know how to take implicit derivatives, and so that's what I'm going to do here. I'm going to take the derivative of p. The derivative of p should be 1, but that's p and not x, so that's dp dx. So I'm utilizing my knowledge of implicit derivatives to take this derivative. The derivative of p should be 1, multiplied by the chain rule, the fact that p is not x, so I need dp dx. Let's move to the right-hand side. The derivative of 10 is 0, no big deal. This is not a product rule because that's a constant in front. In fact, I'm just going to keep the constant in front. Instead, I'm going to take the derivative of the natural log. The derivative of the natural log is the derivative of the inside over the inside. And so there is my derivative. I do pause to see, do I need an extra piece here, times something? The answer is no, because x matches the derivative with respect to. So if you understood your implicits, there's no extra multiplier needed. And so I have found it without much struggle. dp dx will be 50. Well, hold on, let me simplify that. It'd be 50 times 3, so it's 150 over 3x plus 1. That means my rate of change of price with respect to units, quantity, in terms of the supply function. It'd be 150 divided by 3x plus 1, because 50 times 3 is 150. And so from here, once we know that, then we could just go on and answer, all right, and so what is the, rate of change to supply price when the number of units is 33? So we can ask a furthering question, what is the rate of change of price with respect to units if units is 33? If units is currently 33. The answer is no big deal. The rate of change of price with respect to units, that's dpdx. If units is currently 33, that means we plug 33 in. So what we're wondering is, how will price change if we increase 1 unit from 33 to 34 when we plug in? That is, all right, let me plug in 33. 33 times 3 is 99. 99 plus 1 is 100. So we get 150 over 100. What this is my change in units. 150 over 100. Let me just take my calculator so we don't make any silly mistakes with you guys. That's 1.5. And so what I see here is I see a $1.5 increase per unit increase. That's what this is. If you want to increase from 33 to 34, I would expect a $1.5 supply increase in price. So again, just so I make it very, very clear, if we increase from 33 to 34, because that's what the marginal is all about. That's what this derivative has always been about, people. The derivative is all about the marginal, the 1 unit increase. If we increase from 33 to 34, a 1 unit increase, what is the anticipated or expected? So the anticipated increase in price. And that is $1.50, $1.50. That's exactly what you get when you look at the derivative, i.e. the marginal. We're looking at the rate of change. If X increases 1 unit, we're currently at 33 units of supply. If we go from 33 to 34, if we want to go from 33 to 34, what is the anticipated increase in price? And that would be an anticipated increase of $1.50 per unit. Again, once we understand how to take the derivative, and that's what we worked on up here. Once we learn how to take the derivative, now the taking the derivative is not the hard part. What we can spend more time on, once we know how to take the derivative, is understand what it gives me. And what, in this case, we get is an anticipation in an increase in price per unit if we need to increase supply. If we need increased supply from 33 to 34, it's $1.50 increase per unit on supply's end. How would I know that? Because that's what this does. Again, that's what this does. Increase in price per unit for the supply. Thank you guys for watching my video. I hope you stay tuned for later videos on the exponentials. Have a good day.